Okay, next the question is, how do you choose k? Okay, so k equal to 1 means the first, only one nearest neighbor, k equal to 5, you use 5 nearest neighbor. Now, of course, the criterion is going to be what gives you the most accurate predictions. Or it could be, accuracy is not, because error is not, the two errors that we have, false positive and false negative, they both are not equal. Sometimes one is more egregious than the other. So in such cases, then you may want to look at a different metric than simply accuracy rate. So it could be false negative rate. So the lowest false negative rate is what we want, or we want the lowest or the highest sensitivity. So we already know all the different metrics that we have already looked at. So whatever the metric that you want to look at, you look at that metric and see which k gives you the best metric. Okay, if it is error related, you want it the lowest. If it is something accuracy related, you want the highest value. Okay, so which means that you have to try different k. Okay, run the model with k equal to 1, run with k equal to 2, k equal to 3, k equal to 4, so on, and then pick the one that gives you the best, and apply the model to validation set, and then pick the k that gives you the best value. So now what happens when, relatively speaking, so the objective measure is to look at one of these metrics. Okay, there is some subjective concept also is involved. Now when k is very small, okay, you look at only the closest neighbors, so then while you are capturing the nearest pattern, but you may also unfortunately end up with modeling the noise instead of the signal. Okay, so you may be overfitting your model. You're trying to figure out the accurate classification, but low values for k has a tendency to fit where there is no fit available. It's just you're fitting the noise. Okay, so small k will be very volatile, whereas large k is going to be stable. But the problem k, the larger the number of neighbors you take into account, okay, so you may be missing some pattern that's available because you're looking at it from way too high. So you may miss some details that's available only when you look closer. So it's a kind of a balancing game. So low values of k captures local structure but also noise. High value of k provide more smoothing, less noise, but it will miss the local structure. So it's a competing thing, so you have to balance the two. The extreme case, when you say, I'm going to look at the entire data set, so then that's equal to naive rule, which means that whatever the majority case is, you don't even have to calculate distances. If k is equal to n, you simply look at the majority positive event in the train set, and then that's it. That's your predicted class for all the future observations. So whatever k that you choose, you should be able to do better than that. So that's your baseline situation. Okay. So if you have more than two classes, you look at how the proportion of the one class that you are interested in. So if you have 3 classes, but you're interested in one of the 3, then you look at that one that you're interested in. Okay. And categorical variables, okay, remember we are trying to compute a distance, which means all variables will have to be numerical. Right? So you cannot find x sub 1 minus u sub 1 if u sub 1 is a, b, c or something. So you have to, if you have categorical data, you have to define dummy variables for those. Okay. And here, since it is not since it's a parametric, it's not a parametric method. It's not like regression. Okay. You can have m number of dummy variables. Okay, you don't have to do m minus 1. If you have k categories, you have all k dummy variables, not k minus 1. Okay. All right. So if you have numerical outcome, then you would use, instead of majority voting, okay, if you whatever the number of neighbors you have, you find the average of the target variable of those neighbors. If k equal to 1, it's just whatever that y value is. If k equal to 2, you take the 2 y values. Now you have 2 neighbors, average the 2. If you have 3, k equal to 3, then you will have 3 y values, 3 closest neighbor y values, and average the 3, and so on. Okay, advantages and disadvantages. Okay, the main advantage is it's a very simple, straightforward model. Okay, no assumptions needed like normal distribution. Yeah. And it's effective in capturing, there may be very complex relationship between the axis and the target. Okay, but you don't have to worry about any of that because you're looking at neighbors, so it overcomes the complexity of the model because we are not relying on a model. We are simply relying on the closest observations. But there are some shortcomings. Okay, the main one is cursive dimensionality. Okay, so if you have more, we talked about cursive dimensionality in chapter 4, I think. If you have more predictor variables, then the space, the universe in which all the observations reside, becomes, it expands. So the distances, the points become far apart from each other. So that means that you need to have more observations in your data set to be able to have a reliable and stable prediction. So the more predictors, the distances increases because the universe increases. Okay, larger training data is needed, and once you have larger training data, then the computational burden becomes exponentially larger. Because remember, you have to, for every observation, you have to find the distance between that observation on all the cases in the training set. If the training set has 1 million observations, you have to find for every observation that you get, okay, from the validation set, you have to go through all the 1 million observations and find the distance. Okay, so that becomes computationally extremely burdensome. So some ideas to overcome these shortcomings, and that will be, first thing is to reduce the dimensionality. We talked about reducing dimensionality in chapter 4. So you look at categories, you can try to decrease the number of categories, right? Or you can run principal component analysis, and instead of having 30 variables, you can reduce it to like the most important 5 or 6 or 10. So that's another way of reducing dimensionality. And then we have another kind of approach, that is you take the almost nearest approach. So you take variables and you cluster them into clusters of close observations. So if you have 1 million observations, you reduce them to say about 100,000 clusters. Each cluster or 10,000 clusters. So each cluster having like 1,000 observations. All right. So now you compute the distance for the new observation to each cluster, the cluster average. So which cluster is the observation closest to? Then once you find the cluster, then you find the closest observation within the selected cluster. So that way you can reduce the computational burden. So records that are close to each other are grouped into buckets. So the new record, for a new record, buckets are ordered by the distance to the record, and then you select the nearest bucket and then perform the calculations for the nearest bucket. Now, another major shortcoming is once you decide on a K and you implement, okay, when new records come in, you have to go through the computation for the entire training set before you can make a determination. So this could take time, especially when transactions are coming in microseconds. You have to make a call within microseconds, but the computations takes like, a second or something. So then it becomes problematic. So that's why it's called lazy learner. It takes time during production time. So that's the main reason why KNN is not a good idea if turnaround time for prediction is very small. So if you have to make decisions very fast, then this is not a method that is suitable.